Duncan, it's a great pleasure to be in Montreal, if only virtually. I wish I was there in person. And of course, I'm pleased to give the kind of the April Fool's Day seminar, which I think was well chosen by Duncan and Steve. So I'll try to live down to the expectation of the April Fool's Day topology seminar. Okay, so what I'd like to talk about is joint work with Leonardo Ferrari and Sasha Kolpakov, who are at Neuchâtel. I'm going to talk about some recent work on bounding geometrically rational homology three spheres. Okay, so let me just start up with a little bit of background and some motivation. So of course, in geometric and algebraic topology, the study of Bordism properties of manifolds is an important topic. And just to refresh our memories, we say that, you know, M, a closed orientable n-manifold, so the M bounds if there's a W, so that M is the boundary of W. And there's a little schematic drawn here to indicate M is the boundary of W. And we sometimes insist as well that W be orientable as well. So some basic examples of manifolds that bound. So you choose your favorite closed orientable surface of genus G. Well, this bounds a handle body of the same genus. And that's meant to be illustrated by the filled in black stuff inside the blue surface there to indicate that it's bounding the handle body. So that's pretty straightforward. It's a classical result of Rohklin that in fact every closed orientable three manifold actually bounds an orientable four manifold. And indeed, it's another result of Rohklin that the only obstruction to bounding in dimension 4 is the signature of the intersection form on H2 of the manifold. So meaning that, you know, M4 is the boundary of W5 if and only if the signature is 0. And the Bordism group in this case is the whole of the integers. So it's not trivial. So the signature is a genuine obstruction to bounding in dimension 4. And it happens if and only if signature is 0. So this is purely in the topological framework. And the title had the words bounding geometrically. That's meant to indicate a certain amount of geometry that kicks in. And that's going to be in the world of hyperbolic geometry. So let me just recall very briefly definition of hyperbolic manifolds. We're going to be considering only manifolds really in dimension 3 and 4, but we may as well set it up more generally. And in general, it's perhaps most convenient, especially if one wants to describe discrete groups of isometries, to work in the hyperboloid model of the hyperbolic space. So we start with our favorite quadratic form Jn, which is signature n1, n positive eigenvalues and 1 negative eigenvalue. And then we can describe the hyperboloid model of Hn as taking the upper sheet of the hyperboloid given by Jn of x is -1. And then the upper half bit is xn bigger than 0. And we equip this with a Riemannian metric that we get from the Lorentzian inner product given by the form, restricted to the tangent spaces of the hyperboloid. And with this, we get a complete Riemannian metric of constant negative curvature -1. And a full group of isometries of Hn. Well, you might think it's just On1, it's the stuff that preserves the quadratic form, but there's an isometry that flips an isometry of the form that flips the sheets of the hyperboloid. So we restrict to the guys that preserve the hyperboloid. And that's indicated by the decoration of a plus in this particular notation. So that's the full group of isometries of hyperbolic n space via the hyperboloid model. And the orientation preserving isometries is given by the subgroup of determinant 1. So that's the subgroup of O plus n1 of determinant 1. And then a hyperbolic manifold is just simply a quotient of the hyperbolic space by some discrete torsion-free subgroup. So discrete torsion-free means it acts properly discontinuously and freely on the hyperbolic space we can make sense of the quotient space as a manifold then, and it comes then equipped with a hyperbolic metric, and that's our hyperbolic manifolds. And we're going to be interested in hyperbolic 3 manifolds that are closed, and we're going to be interested in hyperbolic 4 manifolds that have these hyperbolic 3 manifolds as totally geodesic boundaries. And I'll say a bit more about that in a minute. Let me just make one comment here that's kind of interesting, although not really germane to what I'm going to talk about today. So as I mentioned a few minutes ago, the obstruction to bounding in dimension 4 is simply the signature. But in fact, one nice thing about hyperbolic 4 manifolds, if you've got a closed orientable hyperbolic 4 manifold, just from the first Pontryagin form vanishing, this in the Hertzebruch signature theorem tells you that in fact, the signature is 0, so they all bound topologically. So any closed orientable hyperbolic 4 manifold bounds topologically. And it's kind of an interesting question to perhaps think about what I'm going to talk about in the context of hyperbolic 4 manifolds bounding 5 manifolds. Okay, so with that geometric setup, here's what I'm going to mean by bounding geometrically. So a closed orientable hyperbolic manifold M bounds geometrically if you can realize it as the totally geodesic boundary of a compact hyperbolic n+1 dimensional manifold W. So maybe the way to say a little bit more about what this is that we're thinking of, that should be an HN+1 here. I just noticed that. I spotted this typo, but I didn't spot that one. So we view the following picture. We have this discrete group of isometries gamma that gives us a quotient manifold W. Now W is going to have infinite volume, as it turns out. It's got this sort of flaring ends off to infinity, but there's this compact convex core here that's bounded by this totally geodesic submanifold M sub n. And so what does totally geodesic submanifold mean here? Well, when we look at the pre-image of this guy M sub n back in hyperbolic n+1 space, we see a collection of codimension 1, i.e. hyperbolic n-dimensional spaces embedded in there, for which the fundamental group of M is acting discontinuously on, let's say, one fixed copy in the pre-image. And being totally geodesic is kind of the nicest possible geometric way for this submanifold to live inside W. And one nice consequence is that, in fact, the fundamental group injects into the fundamental group of W. And so back in the day when we were looking at just bounding, we didn't care one iota about how the fundamental groups behaved, e.g. the surface is bounding a handle body. But here, the totally geodesic is a strong geometric constraint that actually forces strong algebraic constraints on the fundamental group as well. So that's the picture. Yeah.
Yeah, Alan, is this equivalent to saying that M embeds as a totally geodesic separating submanifold of a...
Exactly. You have preempted one of my pictures that will come soon. But as Steve said, exactly, if we now think of just taking this manifold W with this totally geodesic boundary M, then we can double W along the boundary M, and we get this closed hyperbolic manifold for which M is a separating codimension 1 hypersurface. And so in some sense, that's kind of what we're going to be trying to do. Okay, to build guys that bound, it's equivalent to finding embeddings for which the surface is, sorry, not the surface, the hyperbolic manifold is separating. I'm not going to talk about this, but this notion of bounding geometrically was introduced by Darren Lowe and myself in some work that I'll comment on in a little bit. But a natural other setting to talk about bounding is when the manifold in question is a flat n-manifold, so the quotient of Euclidean n space by some Bieberbach group. Now, there's only finitely many such guys in each dimension up to homeomorphism. And it is known that every flat manifold bounds. That's a result of Hamrick and Royster. And one can ask the hyperbolic version of this, namely, say that this flat manifold bounds geometrically if it can be realized as the cusp cross section of a one cusp hyperbolic n+1 manifold W. So the picture we're familiar with as either, once punctured surfaces in dimension 2, or say the complements of knots in S3. And there we kind of look at this torus is occurring as a boundary of a regular neighborhood of the knot. So there are plentiful examples of flat two manifolds. Well, there aren't many flat two manifolds up to homomorphism, but there is the two torus, so we'll look at that one. And I've just told you how to prove that the two torus actually bounds geometrically, because we can construct hyperbolic knot complements in the three sphere, say. But interestingly, this is this sort of scribble down at the bottom left-hand corner, is that there's no known example of a one-cusp hyperbolic manifold in any dimension bigger than or equal to 5. There are construction dimension 4 that are fairly recent, i.e. in the 2012-2013 time period, by Kolpakov and Martelli, they constructed one-cusp hyperbolic 4 manifolds with a 3 torus cusp cross-section. But that's really the extent of our knowledge, and it's kind of embarrassing that we have a plethora of examples in dimension 2 and 3, not so many in dimension 4, and we know nothing above dimension 4.
So are you sort of implying that there should be lots of them?
I'm implying nothing of the kind. I'm just kind of saying we don't know any examples, and I think I'll stop talking there. I'll say a comment later, shortly, that will give some more information about what one has to look for to find these examples. But again, I just really don't know, Steve, what the right framework is. I mean, it is known that amongst arithmetic things, which I'm going to talk about in a little bit, there's no such one-cusp examples beyond dimension 30. So maybe it isn't so common after all. Okay, so let's think about hyperbolic manifolds bounding geometrically. Well, let's think of hyperbolic surfaces bounding geometrically. And for those that have looked at Thurston's notes, they'll have seen at least one example there where Thurston constructs the so-called tripus manifold, which is this knotted Y, it's the complement of a graph in the three sphere, but it has a particular genus true, totally geodesic boundary component. And well, typically a given uniformization cannot possibly bound a hyperbolic 3 manifold. Why? Well, as Steve told me to do earlier, I'll double this guy. And now I've got a closed hyperbolic 3 manifold. And Mosto Prasad rigidity says that the fundamental group of that double now has got algebraic traces. And so the traces of the surface group representing into the fundamental group of the double, this Fuchsian group, that has to have algebraic traces. Now, when we think of moduli space of surfaces, this is some very complicated and countable space. And so there can only be countably many points there because you've got algebraic traces. And so that's an obstruction to bounding a surface on a hyperbolic 3 manifold totally geodesically. And I should say that that's the only obstruction I know. I mean, I don't yet know an explicit example of a uniformization of a surface by a Fuchsian group with algebraic traces that you can prove does not bound a hyperbolic 3 manifold. So in work with Long, we studied this question of hyperbolic 3 manifolds bounding geometrically. And we proved that there is an obstruction to that, namely that the eta invariant has to be an integer. Now, it doesn't really matter what this eta invariant is, it's just some number. But it is an obstruction in this case. Now, the thing about this is that it was proved by Meyerhoff and Neumann that whatever this eta invariant thingy is, it takes on a dense set of values when you do dense surgery on a hyperbolic knot in the 3 sphere. And so therefore, it kind of tells you quite quickly that most surgeries on a hyperbolic knot are never going to bound totally geodesically. And so, this integral obstruction really is a serious business for trying to find examples of hyperbolic 3 manifolds that bound geometrically. And then maybe sort of interestingly as well, that one of our favorite hyperbolic 3 manifolds from way back in the day, one of the first ones constructed, the Seifert-Weber dodecahedral space, well, Francesco Lin pointed out to me that its eta invariant is not an integer. So it cannot bound a hyperbolic 4 manifold, but interestingly, one does know that it embeds inside a hyperbolic 4 manifold. I'll comment on something like this later. Now, there's a similar statement for flat manifolds, and Darren and I constructed examples of flat manifolds that do not bound geometrically in the sense that I described earlier, i.e. they cannot be the cusp cross-section of a one-cusp hyperbolic manifold.
Sorry, by that, do you mean sort of a flat manifold with a geometric structure, or do you mean topologically?
I just mean up the homeomorphism, that's right.
Okay.
So, I mean, it's a nice thing about these Seifert fiber spaces that the A10 variant doesn't depend on the kind of the geometric structure on the Seifert fiber space. So in fact, you know, what we're saying here is that there's a particular flat 3 manifold that's a Seifert manifold, say over the sphere with 3 cone points, all cone angles, 2 pi over 3, that has non-integral A10 variant, and so therefore it cannot bound totally geodesically.
Okay, thanks.
And then the thing that Darren and I did show was that that for every n, there exists closed orientable hyperbolic manifolds that do bound geometrically, and you can even arrange that, you know, the manifold, the n+1 dimensional manifold, is also orientable as well. So there are obstructions to bounding, but they do exist in every dimension. Now, as we'll see later, one of the consequences of the construction that Darren and I gave was that all the examples in dimension 3 have positive first Betti number. And so the question arose, you know, parsing that statement into the next one, do there exist rational homology 3 spheres that bound geometrically? So do there exist hyperbolic rational homology 3 spheres that bound geometrically? So the B1 bigger than 0, we want to get rid of that. We want to have B1 equals 0, i.e. the first homology group is finite, and that's just meaning in dimension 3 because of Poincare duality that it's a rational homology 3 sphere. So that's the question I'd like to talk about today, and in fact, talk a little bit about the proof of this fairly recent work with Ferrari and Kolpakov, that the answer is yes. And in fact, there exist infinitely many rational homology 3 spheres that bound geometrically. And in fact, each of those bound infinitely many distinct, i.e. non-homeomorphic hyperbolic 4 manifolds. Now, what I'm really going to talk about today is a kind of babyer version, just to spare some of the pain and suffering of the arithmetic constructions, that will actually, it won't quite bound in the sense that I described it, but the manifolds will actually land up bounding examples of hyperbolic 4 manifolds that have cusps as well. So these will be hyperbolic 4 manifolds that'll be non-compact. They'll have these cusp ends, but they'll have finite volume. The double would still be a finite volume, non-compact hyperbolic manifold. But we can get examples that come from tweaking the construction that I'm going to talk about, where, again, to spare you the pain and suffering, I'm only going to talk about the field of rational numbers rather than more general number fields, which are finite extensions of Q. Now, maybe one comment to make here is that I mentioned that in the work with Darren, we construct these examples that bound orientable manifolds. Thus far, for various reasons that you'll see shortly, we can only at present prove that our manifolds, our rational homology 3 spheres, bound non-orientable manifolds. And for somebody that basically has tried for most of his adult life to avoid non-orientable things, it's kind of distressing that this is the case, but there we go. We just have to take what God gives us and move on. Okay, so I think that the statement is pretty clear, that what I'm going to try to sketch the proof of. Any other questions at this point? Okay, if not, then I'll move on. Okay, so some comments here, just to kind of focus our minds on what the problems are going to be. Okay, so we've already noted that for these rational homology 3 spheres to bound, the eta invariant has to be an integer. Now, where's our favorite construction of rational homology 3 spheres? Well, by Dane's surgery and a knot in the 3 sphere. most of those fillings are going to be rational homology three spheres. But I told you earlier that that's maybe not a good place to look for candidate rational homology three spheres, because the eta invariants take on a dense set of values in the real. Well, you may be lucky and find one or two sprinkled here and there, but we have to be quite clever, I think you'll agree, in constructing these rational homology three spheres. Now, getting back to the discussion with Steve a few minutes ago, that if the rational homology three sphere or anything else bounds geometrically, then by doubling, we get that M embeds in a closed hyperbolic four manifold. So in fact, maybe the warm-up problem is just simply, well, okay, never mind, let's worrying about, bounding. Let's just, first of all, worry about embedding rational homology three spheres, or even closed hyperbolic three manifolds more generally, inside hyperbolic four manifolds. And again, people have thought a fair bit about this over the last, 20, 30 years or so. And it's fairly delicate, actually, a good deal more delicate than one might think. Part of the problem is that we don't have a rich supply of higher dimensional hyperbolic manifolds. And so if we want to try to embed hyperbolic three manifolds inside hyperbolic four manifolds, that sort of pre-assumes then that we actually know something about the structure of hyperbolic four manifolds, and typically we just don't. And that kind of leads us to kind of the embedding framework. And much to Steve's delight, I'm sure, the words arithmetic hyperbolic manifolds have now appeared in the talk. And the reason is that, the arithmetic machine, and again, I'm not going to get into the nitty gritty of what these things are. I'm going to try and keep this as simple as possible today and just work with things over Q and Z. But the arithmetic framework actually does provide a mechanism whereby one can embed large collections of hyperbolic n-manifolds into hyperbolic n+1 manifolds. Okay, so let's go back. We've got our group of orientation preserving isometries of hyperbolic n space. That's SO plus n1. Now, what's the obvious discrete subgroup of SO plus n1? Well, we just stick a Z in there, and then that's visibly a discrete subgroup of SO n+1. I've decorated with an R here, just because I stole this from a different slide. But anyway, that's a discrete group. And the key thing is that that's the baby example of an arithmetic subgroup of SO plus n1. So the crucial additional information beyond discreteness that arithmeticity provides is not only are you discrete, but in fact, this is finite volume, this quotient that we get by acting. So this group here is not necessarily torsion-free, it's never torsion-free, and elements of finite order. So one gets an orbifold structure in the quotient, but it turns out to be finite volume and it's non-compact for reasons that you can actually maybe see below here, because the example in case n equals 2 turns out to be, well, maybe not the thing you might think it is, like PSL2Z. It turns out to be the 2,4 infinity triangle group, which nevertheless contains parabolic elements. And so the quotient is non-compact. And since this guy lives as a subgroup of SON1, where n is bigger than 2, then we get these parabolic sub-elements in all of these groups. And so therefore these quotients are always non-compact, finite volume hyperbolic orbifolds. Okay, so those are some examples, but how do we get more examples of these arithmetic subgroups? So the trick is to change the form. So these guys here, this guy Jn that I constructed before, that's a quadratic form of signature n1. Well, let me just change that quadratic form by choosing another quadratic form of signature n1. And you maybe just has to fix up some notation. I'm going to think of these quadratic forms as n by n symmetric matrices. And these forms are equivalent over a field K if there's a element in the general linear group over K, so that the T transpose Q1 T is Q2. And I'll just write it like this. So to have signature n1 just means I'm equivalent over the reals to my favorite form Jn. So for example, this guy here, I stuck in a 2 because it's psychologically easier. If you just kind of work out this little bit of silly algebra, you get that, you get this form here. So in fact, over the reals, this quadratic form is equivalent to my favorite form, J2 over the reals. And it's almost equivalent to my favorite form over Q. And there's a little 2 here, but let's not worry about that. Oh, sorry. So this quadratic form Q2 that I've written down here is meant to indicate something different that's going on. My favorite form J2, that represents 0 non-trivially. If you look at the form down here, then I could X to be 1, Y to be 0, and Z to be 1, and that's a non-trivial solution of 0 over the Q. And that means that this form is so-called isotropic. It's isotropic over Q. But if you look at this form here, x squared plus x naught squared plus x1 squared minus 3x2 squared, this guy cannot be isotropic over Q, because a simple bit of algebra then says if that was the case, then you'll end up solving x squared as minus 1 as a solution mod 3, which is impossible. So this guy is anisotropic over Q. But it is still equivalent over the reals to my favorite form, because I can take the square root of 3 in the reals, and that's legal. And so I can make this form equivalent over Q, over R to my favorite form, but not over Q, because over Q, my favorite form represents 0, and this guy does not represent 0. So we're seeing a distinguishing between kind of isotropic versus anisotropic. And then a similar sort of game in dimension 3, let me not spend too much time on this, that this guy is also anisotropic. So we get, because 7 is not the sum of 3 squares, but whenever we get to forms of signature 4, 1, notice that because every integer, positive integer, is the sum of 4 squares, this does represent 0 over Q. And so this form is isotropic. And it's a theorem of Meyer's that, in fact, every form of quadratic form of over Q of signature n1 where it ends at least 4, and again, to have signature n1 just means you're equivalent over the reals to my favorite form, Jn. So every quadratic form over Q of signature n1 where ends at least 4 is isotropic. You can always represent 0, and it's really a sort of more subtle incarnation of every integer being the sum of 4 squares. Okay, now what's that got to do with anything, you may well ask? Well, it's the following. So this is how we can construct arithmetic groups, at least in a special case. So instead of taking my favorite form, I'm going to choose some other quadratic form, Q, capital Q over boldface Q of signature n1. Then I can form this kind of real points. I can take the z points, which is visibly discrete in the real points, and then I can take a special orthogonal group. Those guys with determinant 1. So now that's a discrete subgroup of SOQR. Signature n1 means that I'm equivalent over the reals to my favorite form, which means that there's a transformation that allows me to say T transpose QT is J sub n. Now, what that means in terms of these groups is that the two orthogonal groups are conjugate by this element T. I think I got this in the right place, the inverse. And so this turns out to give us a discrete subgroup of ON1 when we conjugate the Z points. So this is how we construct arithmetic groups. We just basically form this class of objects that we take quadratic forms over Q of signature N1. We build the Z points as I've just given here. We conjugate into ON1, and that allows us to build discrete groups of isometries of hyperbolic n space. And the point is that this is the class of arithmetic groups. Again, it's a special case. You're allowed to change the field more generally, but this will suffice for today's purposes. And the point that I was discussing before was that the form being anisotropic is equivalent to the group being co-compact. So the quotient spaces are compact. And so in particular, when n is at least 4, and we're over Q of signature n1, these groups are always non-co-compact. The quotients always have finite volume but are non-compact. It's only in dimension 3 and 2 that you can construct these real quadratic forms over Q that are anisotropic and therefore get co-compact subgroups of PSL2R and PSL2C. Okay, so that's a special part of the arithmetic machine. Again, I'd like to emphasize here that we know very little about higher dimensional hyperbolic manifolds. We don't expect any kind of hyperbolization theorem. And all known constructions of hyperbolic manifolds in high dimensions come from cutting and pasting arithmetic things. And so these are a kind of key component of how we try to understand hyperbolic manifolds in high dimensions. And in some sense, it's reasonable, given what I've just said, that we look at these guys to build manifolds that embed or bound. But any questions about that? It's a bit hard to take sometimes in a first or second or third viewing.
Is there any easy way a short way of saying why anisotropic is the same as co-compact?
When there's, it's not so easy to say, but I mean, when there's, the way to say it is that when you're isotropic, you can just explicitly build a unipotent element in the group using a solution, a non-trivial solution of 0. The fact that co-compact is equivalent to anisotropic is a little bit deeper than that. Thanks, Duncan. Okay, so we cast our minds back a little bit. We were trying to think about embedding as a warm-up problem. And one of the reasons that these manifolds are interesting is that sort of we can solve the embedding problems in a particular situation. Namely, when we take one of our quadratic forms Q with coefficients in Z, we take some hyperbolic manifold that we constructed as in the previous page. Again, I'm being a little bit of abusive notation by sort of saying that it lives here and taking the quotient of hyperbolic n space. There's some conjugation there, but fear not about that. But the point is that if we can arrange this M, so with a gamma living in the Q points, then that manifold embeds in a finite volume arithmetic hyperbolic n+1 dimensional manifold. And you can even arrange that this guy is orientable. So this is a good first step. We've kind of proven that one place to at least embed manifolds is to start looking at these arithmetic manifolds with these special properties. And the proof of this, again, uses some fairly sophisticated machinery, even though the idea is pretty straightforward. I'm not going to get into it. But it uses a kind of virtual special cube complex machine. And the point is that these arithmetic manifolds were proven to be virtually special by Bergeron, not the one that's at UCAM, Haglund, and Wise. And that is the one at McGill. Now, as I just mentioned, getting back to the point, so in this particular case, the setting I've described here, the manifolds that we're constructing that are the n+1 dimensional manifolds, these will be non-compact because everything's over Q. So I've got this hyperbolic 3 manifold, I embed it inside some hyperbolic 4 manifold, but because of the discussion I had earlier, this hyperbolic 4 manifold has got cusps. And so, that's just what we have to live with right now. So the red text here basically kind of says that you can change this by letting the field vary, and then you can get genuine closed hyperbolic manifolds that you get as the target n+1 dimensional manifold. Okay, now as we've alluded to at several points, there's two flavors of embedding now. There's the separating embedding and the non-separating embedding. Now, for most of my adult life, I preferred the non-separating embedding because we wanted to prove things that had positive first Betty number in finite sheet covers. But thanks to Egel, I've given all that up, and then I'm starting to look for things that have separating embeddings. And so, in the context of bounding, this is what we want to see. We want to see this manifold embedded and separating. So we want now to develop some technology that recognizes when a manifold is separating inside some higher dimensional hyperbolic manifold. And so this is what Darren and I did originally. So here again, using the kind of the arithmetic machine, what we noticed was that if you start with that manifold M, it's orientable arithmetic, and it's a double cover of a non-orientable manifold, and you run this kind of machine that I just described so that the non-orientable manifold embeds in an orientable n+1 dimensional manifold. And you can use this embedded non-orientable manifold to get a homomorphism to Z mod 2Z, for which the orientation double cover then embeds as a separating submanifold in the double covered W2 corresponding to the kernel of that homomorphism. So that's a nice cheap trick to arrange that these orientation double covers of these non-orientable manifolds do indeed bound totally geodesically. And that's kind of was at the root of how we were able to construct examples in every dimension. We just kind of ran that kind of machine in a more primitive version that I had with Kolpakov and Slavich, and was able to kind of construct these examples. Now notice that this is the reason that you know, for Darren and myself, the three-manifold version of this that we constructed always has positive first Betti number, because in dimension 3, if you're in a non-orientable three-manifold, it's kind of simple homological algebra. It just shows you then that the first Betti number of that non-orientable manifold is bigger than 0. And so therefore, the first Betti number of my orientation double cover is also bigger than 0. So we're not going to be able to apply this version to get rational homology 3 spheres. And in fact, because the examples we construct have the property that they admit a free orientation reversing involution, that means that their eta invariant turns out to be 0. It's just a property of eta. So in fact, it turns out that we, as far as I know, we still don't know an example of a manifold that bounds geometrically for which the eta invariant is not 0, but an integer. So all known examples have eta equals 0. I don't know about the examples I'm about to tell you about. Okay, so that was the construction with long. And in some sense, what I'm going to tell you now is an extension of this idea that, you know, we have to live with the fact that the embedding is non-separating, but you see, if we can arrange that we have a manifold that's orientable, hyperbolic, and admits a free isometric involution, orientation preserving or reversing at this point, then if it embeds geodesically, then in fact it actually bounds geometrically. So the previous case in some sense was the orientation reversing involution. And now what I'm saying here is that in fact, even if it's an orientation preserving involution, you can do something that's kind of a standard trick in geometric topology where you just sort of quotient out the boundary or one of the boundary components. So the point is that we've got this manifold M that we've embedded inside some hyperbolic n+1 dimensional manifold. We may as well just assume that it's non-separating there because we're happy if it is not non-separating. And so there's the picture when we cut open, we see 2 copies of M, one red, one blue. And we've got this free involution tau. So we can use tau to quotient out the red copy. Okay, so we just kind of do a self-identification of M using tau, and it gets folded up inside. And this is the schematic that we've drawn down here. And so that what we see is a manifold with a single blue component that is now M. Now, the issue is that tau is an isometry, so this quotient space is a hyperbolic manifold, but if tau is orientation preserving in the time-honored tradition that we know from algebraic topology, because it's orientation preserving here, this manifold is going to be non-orientable in the quotient, so we can't match things up when we do the gluing on the boundary. And so that's the trick that we're going to use as the extension of the work with Darren. Okay, so now the task is we have to find these rational homology spheres. We've kind of forgotten about the eta invariant stuff. We just want to find rational homology spheres that embed inside arithmetic hyperbolic n+1 manifold, or 4 manifolds in this case, and the admit involutions. Now, again, that's not altogether straightforward. Okay, so here's what we're going to try to do. We're going to try to embed rational homology 3 spheres, admitting free involutions into hyperbolic 4 manifolds, imply lemma B. And in case I forgot to say it, lemma B was this one, and it's B for bounding. So I can cunningly arrange that lemma B would be bounding. Okay, so the lemma C that we need to prove is the following. Now, there's a lot to take in this. And then maybe the first thing to comment on is, if you look at this arithmetic rational homology 3 sphere with gamma inside the Q points of a quadratic form. So already, you know, that's another task that we have to arrange. How do we find such a thing? Now we know there are lots of arithmetic rational homology 3 spheres. for example, the Weeks manifold. In fact, the first three smallest hyperbolic three manifolds are all arithmetic rational homology three spheres. Unfortunately, none of those fit this framework. So there's kind of work to do that I'll address shortly. But we need, in addition to being arithmetic rational homology three sphere with this algebraic condition on Q points, then we needed to have the following properties. It's residually P, so it just simply means that it's a strengthening of residual finiteness, that there should be for every non-trivial element gamma in the group, there should be a homomorphism to a finite P group for which phi of gamma is non-trivial. Gamma is so-called P powerful that I'll come back to in a minute, and I'll talk about that, for some odd prime B. And this is a condition that gives us control on towers of P power index normal subgroups that can be traced back to work of Mann and Lobotsky and p-adic analytic groups. There should be a double cover M prime over M, which is also a rational homology three sphere. So this is where we're going to get the manifold with our free involution. That's also P powerful. Now whatever this P powerful business is, it's kind of, doesn't typically behave well with respect to subgroups of finite index, as we'll see. But anyway, we need that property, whatever it is, to persist in that subgroup of index 2. And then if we can arrange all of that, then there'll be a tower. So we get this infinite descending chain of finite index normal subgroups in delta, which are all going to be P power index, that will all admit an involution. And these guys will all bound geometrically a hyperbolic four manifold. And again, as I mentioned before, for reasons of the rational construction, these will all be finite volume but non-compact. But again, there's a souped up version that we can use to give compact cases. And moreover, again, running the proof of this theorem A with Kolpakov and Slavich, we can get infinitely many non-homeomorphic guys with the same boundary, i.e. with n sub j as the boundary. So there's a lot to take in this screen, I understand that. But you'll see where this comes from in a moment. So, cast your minds back many, many years when we were living in a state of ignorance about, well, what do we know about rational homology three spheres? And it was a question of Cooper as to whether there exists rational homology three spheres of arbitrarily large injectivity radius. So the groups are residually finite. So, the tower of all finite index normal subgroups intersects in the identity. And what the Cooper question is asking is, can you go down that tower and somehow keep finding rational homology spheres as you weave yourself down the tower? And it's not quite what he asked, but that's one way to think about it. So let me just kind of say that this was answered by Caligari and Dunfield, and this is Caligari the Younger and Dunfield, in a paper where they constructed towers of rational homology three spheres that use this P powerful technology. And so for an odd prime P, a finite P group that's called powerful, and this is a definition that goes back to Lobotsky and Mann, if the quotient of S by the Pth powers is abelian. Again, it's kind of not easy to explain why you might care about this, but I mean, this is a natural kind of structure that one sees when one starts to think about p-adic analytic groups and distinguishing groups whose pro-P completion is and isn't p-adic analytic. And this is kind of the condition that's helpful to that. And then a finitely generated group, this is what I was really alluding to, is P powerful if every finite P group quotient of gamma is powerful. So the P group quotients of gamma are all of this particular form. They're all powerful P groups. Again, it's a bit much to take, but the crucial thing is that in a fairly general setting, Caligari and Dunfield in their paper that I'll mention shortly, their construction of these rational homology three spheres that answered Cooper's question was conditional on GRH and part of the Langlands program. This was removed by Boston and Ellenberg, who brought in this pro-P technology and kind of use this notion. They didn't quite say it like this, but Caligari and Dunfield reformulated what Boston-Ellenberg did in terms of this P powerful. So there's a general kind of statement that says gamma finitely generated, which is P powerful. If a Booleanization of gamma is finite, then in fact, this P powerful condition, you get finiteness on any subgroup H of P power index. So that's a very strong statement. Okay, you want to construct rational homology spheres in a tower of finite index subgroups. This is a way that one does it. Okay, there's things to check that, you know, you've got to prove that something's P powerful, but in fact, it turns out that's not quite so bad as you might think. And as I allude to down here, really, it's reduced to just using magma. So that you can test for P powerful using the computational group theory package magma. So this key lemma is a very useful tool for establishing rational homology 3 spheres. And again, I emphasize, I don't know how to give a geometric proof of Cooper's question to construct rational homology 3 spheres of orbitally large injectivity radius. The only constructions I know of use these methods that come out of Caligari and Dunfield and Boston and Ellenberg. So I think it's a great challenge question to try to do that. Okay, so let me talk about the proof. So you've probably forgotten exactly what the statement of the proof was. So the statement of the theorem was, but that's okay, because I'm going to tell you. So the first thing about gamma was it was contained inside the Q points. That's going to be relevant to apply theorem A. The hypothesis was that gamma is residually P. So that means that we can descend to the identity in a normal P power index subgroup chain of subgroups. So that's one way to think about residually P. And so since gamma is P powerful, that was the assumption, the key lemma of Boston, Ellenberg, Caligari, Dunfield now tells me that all of these guys here in this chain are all rational homology 3 spheres. Now, we said that they have this M prime that was a double cover of our manifold M. It was also a rational homology 3 sphere by assumption. So we have this group delta, whose first homology group is finite. It's got indexed to here, all these blue indices on the right-hand side. These are all P power. And so we get a chain that I'm calling delta N, where we intersect delta with gamma N. These all turn out to be normal subgroups of P power index as well, because P is odd. And again, the P powerful statement of delta, that was also part of the hypothesis, says that all of these guys are then rational homology 3 spheres. And so now we've got towers of rational homology 3 spheres, and it's the green tower that I like, because those are the guys that admit an involution. Those are the guys I can apply lemma B to. How do I have to apply lemma B? Well, I have to embed them somewhere. Well, the good news is I arranged that these guys lie in the Q points, so that theorem A, that worked with Kolpakov and Slavich, allows me to embed these guys inside higher dimensional or 4-dimensional hyperbolic manifolds in this case. And then we apply lemma B to get bounding. So all of these green guys here, these all bound hyperbolic manifolds. And as I said, they're all non-orientable, but it is what it is. So that's how all the pieces kind of fit together there. Again, if you haven't seen Boston Ellenberg or Caligari Dunfield, I mean, the Boston Ellenberg is a beautiful idea that captures the essence of this P powerful. And let me kind of just say one thing about, you know, what's sort of incredible about these kind of rational homology 3 spheres. So the expectation is that they're all rational homology 3 sphere. That was proven, but the torsion is just exploding in growth. I mean, you know, there's kind of conjectures that say what's going on there. So the torsion is just growing, you know, really, really quickly. But in fact, the mod P homology, and this is the crucial point about the P powerful assumption, has always got rank 3. So all of these guys, delta 1, etc., all of these guys, gamma 2, etc., they all have mod P homology that just looks like ZP cross ZP cross ZP for this odd prime P, all the way down this chain. And that's kind of a crucial part of when you take the pro-P completion of these groups, it turns out to be p-adic analytic. And that's kind of the crucial kind of connection that, you know, Boston and Ellenberg saw between the pro-P role and proving rational homology 3 spheres. Okay, so that's the proof of the theorem. But of course, I have to promise you examples. Well, I alluded to some examples, and it's the examples of Caligari and Dunfield. So the form in question here, even though if you look at their paper, you will not see this quadratic form anywhere. There's words involve quaternion algebras over number fields and stuff like that. People that have heard me talk before have heard me say those words. I haven't said them until now. But the point is that these quaternion algebras over number fields, in this case, can be interpreted as groups of quadratic forms. And this is the quadratic form in question in this case. And what the paper of Caligari, the Younger, and Dunfield do is they construct this tower fairly explicitly here, so that, you know, each of these quotients are very controlled. They're either Z3 cross Z3 or just Z3. And in particular, the intersection being the identity here of these tower of normal 3-power index subgroups means that gamma is residually P. And then they show, again, conditional on GRH in the Langlands program, that these guys are all rational homology 3-sphere. And as I said, the crucial input of Boston-Ellenberg was to notice that this powerful technology could be brought to bear to show that gamma 2 is 3-powerful, and then get that this is a tower of rational homology 3-spheres. Okay, that's one tower, but now you'll notice that I still need a double cover of something. So then we've got some more work to do. So in fact, the rational homology 3-spheres that bound in this case are actually double covers of this tower. Now, why do I know these double covers exist? Well, it's because you have to appeal to magma at this point. Well, I mean, maybe smart people can just do this by hand, and Dunfield have done it in his head by now. But anyway, you can use magma to compute that M2, this guy in the tower, is a manifold that has got this homology. Notice the mod 3 homology is just Z3 cross Z3 cross Z3. And in particular, there are 7 subgroups of index 2 to choose from. And in fact, we choose one there to set as the group delta that allows us to build the second chain of the deltas that actually correspond to the manifolds that bound geometrically. And, you know, for what it's worth, here is kind of the magma information. So now the point here, gamma 1's no good because there's an element of order 3 there. So that's where we have to pass to gamma 2 to get started. And then we've enumerated the subgroups of gamma 2. And notice that, in fact, the first guy that of index 2 has this kind of property, where the Z3 homology is quite complicated. So this guy turns out not to be 3-powerful. But we like this guy. This guy here turns out to be 3-powerful. And 3-powerful can be checked using magma. I'm not going to get into that, but it's not so bad. But that's the crucial thing. You know, this guy has got mod 3 homology rank 3, and that's what persists in this business. So it's this double cover of the chain of the examples of Caligari and Dunfield that allows us to construct these rational homology spheres that bound geometrically. Okay, I promised infinitely many, maybe I won't dwell on that. If you go into the construction with Kolpakov and Slavich, there's various quadratic forms of signature 4-1 are built from a signature 3-1 quadratic form. Namely, we have a form Q that we got from Caligari Dunfield, and we just construct additional forms of signature 4-1 just by summing on a particular term. So that part's not so hard once you see what to do in the proof of the theorem A. So let me not say too much about that. One can get examples of compact guys, sorry, closed guys that bound compact hyperbolic form manifolds, and it's a similar game. You have to sort of soup up the number field and then go to find examples. So here, there's a particular tower of examples that are 11 powerful in this case, that allow us to construct rational homology spheres for which the mod 11 homology is totally controlled. It's kind of a cool construction, exactly, actually. Anyway, one can do that. Let me just finish off by maybe sort of saying some final comments that one might wonder about higher dimensional hyperbolic manifolds. Well, there can be no rational homology hyperbolic manifolds in even dimensions of the form 4k plus 2 just because of the Euler characteristic is 2, but then the volume would be negative if we had in that case, which is illegal. And when we're dealing with arithmetic manifolds for n bigger than 5, there's no arithmetic rational homology spheres. So, you know, that's a problem if we want to kind of try to do that in higher dimensions. And then, well, maybe they exist in dimension 4. We don't know that yet. But if they do exist, they actually live in a very special commensurability class of arithmetic 4-dimensional manifolds coming from this auxiliary group. And so with that, thank you. We're seeing I'll end there. Thanks very much.
Thank you, Alan. Are there any questions?
I'll have one. So as far as I understand the construction, you really don't have any flexibility to get an orientable.
No, exactly. So it's going to take something new again to actually get an orientable one. That's correct.
Yeah, you're completely scuppered from any way you want to try.
That's right.
Yeah, in that construction. Yeah.
Exactly. And then you really are struggling, because if this is something I'm embarrassed to say, that it only kind of dawned on me late in life, that it's actually quite hard to tell if if you're just building things, you've got things explicitly and you kind of say, aha, okay, how do I test something as separating or non-separating? Well, if it's non-separating, if you can find a loop that has got intersection number 1 with that submanifold, then you're happy. It's non-separating, you can certify that. But if you're just embedding things in the way that I've been doing recently, it's kind of hard to kind of give me a condition that says that this guy separates. And I've given you some conditions today, but beyond that, it's kind of hard to know what to do, actually.
Mm-hmm. So what about, look, this is the most interesting case, I think, in the three-dimensional geometric bounding 4 dimensions, but what about other types of geometric structures on 3 manifolds, bounding geometric 4 manifolds? Does that make sense?
Yeah, no, that makes sense. I mean, one could just stick in the world of hyperbolic things and kind of do what we do in dimension 3, right? So we could, we have lots of embedded surfaces around, and it's a rare day that they're totally geodesic. So we can certainly find examples of, quasi-Fuchsian structures on the surface that bound hyperbolic 3 manifolds. And so one could look for deformations of a hyperbolic structure on hyperbolic 3 manifolds that would bound a hyperbolic 4 manifold. And again, I don't know what to say much about that. I mean, there is a notion of geometric structures in 4 manifolds, kind of a la Thurston. And there's, a bit, I forget the number of them now, but there is a notion of geometric structure, and they've been enumerated. And one could start to think about looking at these geometric structures in 3 manifolds and asking to embed those guys inside these other geometric structures in 4 manifolds, and trying to see if there's any interesting sort of bounding phenomena. I mean, one could also try to think about, these hyperbolic 3 manifolds that bound these hyperbolic 4 manifolds. Well, of course, people in the symplectic and contact world kind of love things to bound for various reasons, but that doesn't seem to play well with any of the stuff that we kind of know what to do.
Well, but what do you mean by that? For instance, symplectic.
Right. So
hyperbolic manifolds just not symplectic?
We don't know. So it's still open as to whether a closed hyperbolic 4 manifold is virtually symplectic. I think the guessing would be, if you were a betting person, and I know nothing about this, is that they are not virtually symplectic, because the conjecture is that all Seiberg-Witten invariants vanish. And so, again, the fact that people don't know much about kind of Seiberg-Witten theory for these hyperbolic manifolds, I think, is a testament to the fact that negative curvature doesn't seem to play well with that set of equations.
Mm-hmm.
May I ask a question, please?
Sure.
Thank you for the interesting talk. It's just, can you give some intuition for the proof of your theorem with Long, which says that a 3 manifold bounds a 4 manifold, then the eta invariant of the 3 manifold must be integral? Just because eta invariant is constructed out of the Laplacian and its eigenvalues, so it's difficult to see the connection between Bordism.
Right. So you're exactly right. But the good news for Long and myself, because we know nothing about the Atiyah-Pitotti-Singer index theorem, is that the Atiyah-Pitotti index theorem says, roughly, right, there's some integral over Pontryagin classes, there's a signature, there's some, the eight invariant, and then there's some correction term.
Right.
Now, because we're hyperbolic, the Pontryagin classes vanish, so that disappears. The signature is an integer. That's where the integer comes from. This correction term, you know, whatever it is, it involves the second fundamental form of the stuff at the boundary. Now, all I know about such things is totally geodesics guys have second fundamental form that vanishes. So we don't have to worry about doing any analysis whatsoever. And so that tells you the eta invariant is an integer because everything else is zero. That's kind of how the proof goes.
Cool. Thanks. That was very neat. Thanks.
Yeah, it is very neat, you know, especially because, you know, doing any analysis just scares the living daylights out of me. So it's...
And I guess, so is this also true if the 4-manifold is non-orientable? The bounded manifold is non-orientable?
No, I don't know that. So the APS only works for oriented guys, as far as I know. Others might know better.
Okay. Thanks.
Sure.
Okay. Well, if there are no further questions, let's thank Alan again.
Yeah.